Hello and welcome back to the FPGA PS channel. In today's video, we are going to talk about the Xilinx Gigabit Ethernet. So consider this scenario. You have some source of the data like analog to digital converter or camera that is writing into this TX buffer in the DDR memory, and your target is to transfer those data to your host machine for the visualization or for further processing. Or you have some data in your host machine and you want to send it into your embedded system. And you are also targeting to use the Gigabit Ethernet standard as the interface protocol. To make it more interesting, we want to run this Gigabit Ethernet today in the 7 series FPGA board, and since there is no ARM core, we need to utilize the MicroBlaze. And also MicroBlaze doesn't have any peripherals. It doesn't have any hardened Gigabit Ethernet. So we need to use the Gigabit Ethernet. We need to use the AXI Gigabit Ethernet IP core in the FPGA side of our design. Let's look at our buffered data with the more detail. So again, we have TX buffer that we want to send it over the AXI Gigabit Ethernet to the host machine. And we also have a RX buffer that our target is to receive the data and write them into this RX buffer. So we don't want the CPU to be involved and send the data one by one from the DDR memory to the AXI Ethernet. So in this case, we use the AXI DMA. AXI DMA make the ease of the job for the CPU. It minimizes the involvement for the data movement, and the CPU can do the most important job like the data processing or controlling. So the AXI DMA will be the interface that they grab the data from the DDR memory and send them to the AXI Ethernet. So we also have the MAC in the AXI Ethernet IP core. That's why I also show the MAC beside the AXI Ethernet. The CPU also controls the AXI Ethernet. So the main job of the CPU, that it could be ARM core or it's a MicroBlaze, is the control and monitoring. So the AXI Ethernet is the bridge between the data that the AXI DMA is delivering from the DDR memory to send them to the PHY. Whenever that we want to send the data from the digital layer to the physical layer, we need to have the PHY, and the PHY will translate the digital data to suitable data for that physical layer that we have. Between the AXI Ethernet and between the PHY, there are two groups of the different pins. The first group of the pins is the RGMII pins. Those pins contains the RX data, TX data, they contains the data lines, and we also have the MIO pins. MIO pins, like the I2C, they are there for the communication between our AXI Ethernet IP and PHY. And by the help of them, the AXI Ethernet IP, it can set up, it can configure the PHY chipset, and it can also see and monitor the status of our PHY. And then PHY will directly connect it to the RJ5 connector. So for sure here, because we are going to work with the 7 series again, we need to have the MIG memory interface generator, and then we can have access to the PL DDR memory. So in this slide, I'm going to have an overview of the block diagram of the Vivado design. So first of all, I want to divide the MicroBlaze buses into the three different groups. The first group is the local memory bus, and these two buses, data and the instruction, are connected to the local VRAM memory as the local memory over the VRAM controller. So the first section that we can see here is the local memory buses that they are connected to that block memory. We will see all of these sections in the Vivado design. The next section that we have is the master AXI, data, and the peripherals. And as you can see, this bus will be used to connect the MicroBlaze to the other peripherals that we have in the design, like the AXI UART and AXI timer, and it will be used also to control the AXI DMA and AXI Ethernet. The third section, the third group of the buses that we have is for the data cache and instruction cache. And this instruction cache and the data cache, by the help of the MIG, is connected to the DDR. It allows the MicroBlaze to have access to the larger amount of the memory rather than this small amount of the DRAM. And this is necessary for this design because we are going to run the FreeRTOS and LWIP, and those are the big application, and the amount of the memory that the DRAM give to us is not enough, and we will have access to the DDR memory. So the third section that I want to explain is the scenario that we have to connect the AXI Ethernet to the MicroBlaze. So as you can see, the control to the AXI Ethernet and the AXI DMA is given to the MicroBlaze by the help of the data peripheral and this AXI interconnect that connect the AXI slave ports of the AXI Ethernet and AXI DMA to the data peripheral port of our MicroBlaze. And you can see here that AXI DMA, one side is connected to the DDR memory, as you can follow here, and from another side is connected to the AXI Ethernet. So it will read and write data from the DDR memory to the AXI Ethernet. And that AXI Ethernet will work at the bridge and deliver the data to the PHY, or will deliver the data from the PHY to the AXI DMA to transfer them to the DDR memory. And our PHY is also connected to the RJ5 connector. So we also have a debug module here. The debug module is there to allow the Vitess application to debug and download the application into our MicroBlaze. And we will run the FreeRTOS and LWIP that I will explain it in the next slide in our MicroBlaze processor. I already created the Vivado project for the RTX 7 AC701 evaluation board. And since I'm using the evaluation board, I will have much more options that make my job much easier. So I'm going to open the block design, and then I will move to the board window. In the board window, multiple examples that they are ready to use are provided from the Xilinx. For example, the first thing that I'm going to use is the MIG DDR. So I will grab the MIG DDR and I will add it in my block design. As you can see, the Vivado automatically connect the MIG to the right pins for me. If you also open the MIG, you will see that the Vivado automatically configured the MIG for me based on the datasheet and the user manual of the board. If I want to do it all of these steps manually, I need to first carefully study the user manual of the AC701, and also I need to set up and configure all of these clocks and the option so carefully. But here Vivado fulfilled all of these difficulties for me. We have our MIG DDR memory and we are going to add the MicroBlaze into our design. As soon as I add the MicroBlaze to the design, I can see that the run block automation appear on the top of the Vivado. So I can use it to configure my MicroBlaze. So for the preset, I'm going to use the real time since I'm going to work with the FreeRTOS. I'm going to have the local memory of the 16 kilobyte. I think it's enough for me. As you can see here, the cache configuration, since I selected the real time preset, is also selected for me, and I will have an 8 kilobyte of the cache configuration. For the debug mode, we will use the debug mode only, and for the peripheral, I also need to enable it because as I showed that before, the AXI timer and AXI UART will be connected to the peripheral port. It also wants to connect the clock of the MicroBlaze to the one clocks of the MIG, and I prefer to use the UI clock. So let's have a look at what Vivado Block automation completed for us. As you can see that the local memory bus is completed and is connected to this block memory generator by the help of the two DRAM controller that I have here, and it also connected the MicroBlaze debug module to the debug port. If for the moment I compare it with this block diagram that I have, I can say that the first section of the buses are done for now. Another important point in this design is that we will use the UI clock from the MIG as the clock for all the peripherals and for all the IPs that we have in this Vivado design. I also highlight it so we know that this clock is the main clock for our design. We also have one reset. We also have one reset that is provided by this processor system reset and is synchronized to the UI clock, and we will also use it for the synchronized reset for all the IPs that we will add in our Vivado design. The next section that I want to complete is to connect the data cache and instruction cache buses to the MIG interface that I have. So in the AXI interconnect, I need to have two slave port and one master port. And then I connect the master port of AXI interconnect to a slave port of the MIG, and it allows me to connect the two slave port of the MicroBlaze to the MIG, and then it will interface to the DDR3 that I have in the board. So if we look at the block diagram, we can say that this section is also completed. The next section that I want to complete is to add the peripherals that I need to the MicroBlaze. So I'm going to add the AXI UART from the board window again. Again here, the Vivado will automatically first set up my UART. It will choose here the RS232 UART. And for the IP configuration, it will use the clock frequency equal to the 100 MHz. And I want to set up the rate to 115,200. So I added the UART, and I can see that it also connected to the right pins. Since we are going to run the FreeRTOS, we need to have a timer in our design, and I'm going to add the AXI timer to the design. And then we need to connect these two IP cores to the MicroBlaze. And we will use the AXI data peripherals as I mentioned it before in the presentation. So I will add another AXI interconnect, and I will use it to connect my peripherals to the AXI data. So we can say that this section to connect the other peripherals to the master AXI data peripherals is also done. Now we are going to connect the clock of all the IPs that we have in our Vivado design to the user interface clock from the MIG. I connected the clock of all the IPs, and now I'm going to use this reset pin for all the IPs that I have in the Vivado design. I also connected the reset pin of all the IPs, but we still have another system reset pins. Usually the system reset pins, it's connected to the push button, to the external reset. It's connected to the push button that we have in our evaluation board. So I'm again going to the board window, and I will grab the FPGA reset and connect it to the system reset that I have. So you can see that the system reset of the MIG is connected to the reset pin of our evaluation board. Until now, we completed the three main sections: the local memory bus, the MIG connection to the DDR, and connection to the AXI UART. And now it's the time to add the AXI Ethernet IP core to our design. Again here, I'm going to use the provided example in the board window. So I will grab the onboard PHY. That's the one example of the Ethernet configuration. I will grab the onboard PHY and I will add it to my design. So as you can see here, the Vivado connected already my MDIO pins, RGMII pins, and also the PHY reset pin. If we look at the configuration of this block, we can see that the IP interface is RGMII, and it will use the MDIO MDC to connect the AXI Ethernet to the PHY, and the physical layer speed is configured at the 1 gigabit per second. It's going to use the RGMII, and please note that the MAC is implemented inside the PL side as the soft MAC. It's completely implemented in our FPGA fabric. We added the AXI Ethernet IP in our Vivado design, but still we need to add the AXI DMA and other section that those are necessary to connect our AXI Ethernet to the buffer as I explained it before. So I'm going to use the run block automation, and as you can see here, I will choose only the AXI Ethernet. So the physical interface is selected as the RGM2, and another important point is connect AXI streaming interface to DMA. So it will add the DMA, it will configure the DMA, and then it will connect the AXI IP Ethernet by the help of that DMA to the MIG interface. So the AXI DMA from one side is connected to the AXI Ethernet, and from another side, as you can follow these two ports, is connected to the MIG, and the MIG connect the AXI DMA to the DDR3 memory. So we also completed the last section of our design to add the AXI DMA and AXI Ethernet IP core. Please note that to run the AXI Ethernet, we need more clocks. The first clock that we need is 125 megahertz. As you can see here, the first clock is 125 megahertz, and the second clock that we need is 200 megahertz clock, and is connected to AXI stream clock and also the reference clock. Vivado also added another processor system reset to generate a synchronized reset with the clock 200 megahertz here. I need to connect the external reset in to another FPGA reset pin that I added previously in my design. Now I'm done with that external reset connection as well, and now is the time to connect the interrupt to the MicroBlaze. We need to route all the interrupts that we have to our MicroBlaze. To do this, I'm going to add AXI interrupt controller, and then connect the interrupt port to the interrupt port of the MicroBlaze, and we add another port to this AXI interconnect. Then we connect the new master port to the slave port of the AXI interrupt controller. I want to let the Vivado to complete the clock and reset connection, as you can see here. And then we add concat IP to our design. We have 5 different interrupts that we need to route them to the MicroBlaze. So I increase the number of the ports of the concat IP to the 5. And I will connect the interrupt from the UART, AXI timer, AXI Ethernet, and AXI DMA to the input ports of the concat, and then it will be routed to the MicroBlaze. We are almost done with the Vivado design, and we need to validate the block design. After validation, Vivado will assign all the necessary addresses to the peripherals that we have in our block design. It's good also to check the address editor to see if there any addresses is missing. And as you can see here, the MicroBlaze has access to all the peripherals that we have in our design. Finally, we need to add the top wrapper to our design and let the Vivado to manage and update it. Now we can run the synthesis and wait until the synthesis is finished. After synthesis completed, open the synthesized design and then go to the I/O port. If the I/O port is not opened here, you can open it from the window I/O ports. I already studied the AXI 701 evaluation board user manual, and I took some screenshot from the important pins that I want to review with you here. For example, one of the pins that I want to review is the MDIO MDC. As you can see, it's connected to the MDC MDIOI, W18 and the T14. And in the user manual, it's also mentioned that the MDIO MDC is connected to the T14 and W18. During the Vivado design, I used the examples from the board window. Then I didn't need to adjust all of these pins. However, If I didn't use the board designs, if I didn't use the board examples, then I need to come to the synthesis design, and then I need to assign all the ports manually to the right pins. Another one is the RGM2. As you can see here, the RGM2 is connected to this group of the pins, and if you look at to the user manual, you will find the same pins are mentioned. The next one is the UART. You can see here the UART is connected to the T19 and the U19. And if we look at the user manual, the same pins are used for the UART connection. Another one is system differential clock. As you can see, is connected to the R3, and based on the user manual, R3 is the system clock that we have on the board. After we completely assign the right pins to our port, we can proceed and generate the bitstream. Bitstream generation is completed. I want to go to the report and have a look at the timing and see how much resources of the FPGA is utilized for this design. As you can see, we have some timing error because we are working with the RTX family, and around 20% of the resources are used to run our MicroBlaze. The last thing that we need to do in the Vivado is to export the hardware to use it later on in VTest for application design.